Okay, welcome to week 2, part 2. In this lecture, we're going to take a look at how to develop programs, how to deal with user and file input, and also produce file output. And we're going to take a look at how to define and call functions. We already know several important things. We know how to create and use variables. We know how to deal with arithmetic computations involving a combination of int and float values. We know a couple of forms of sequence data types, namely the stir and the list. We know how to loop through the items in a sequence using a for loop. We also know about slicing sequences, concatenating sequences with plus, and repeating multiple occurrences of a sequence with the star operator, the times operator. We've also taken a look at relational and logical operators in the context of decisions involving the if, elif, else decision structure. So, almost, we know how to write programs. At least all small programs of the kind that we're going to be writing in here follow a fairly straightforward outline. First of all, they get some information, some data from somewhere. That might be from a file, it might be from a user, or from a database, or what have you. They process that information in some way, sorting it, counting it, computing statistics, generating graphs from it, or various other kinds of reports. And finally, they produce some useful output that the user can look at and use to make decisions. In fact, as a sort of historical sideline, HIPO, which stands for Hierarchical Input Process Output, was an early top-down approach to software design. And for the small programs that we're going to be writing here, we'll just go ahead and use that. Any kind of formal methodology, no matter how simple, is better than no plan at all. Okay, so where are we going to get input from? Well, one obvious place to get input from is from the user by means of the user's keyboard. We can also read data from some kind of file. We can do what's called web scraping and pull down data from some remote website. Possibly we're writing a program that is reading data from some kind of sensors, temperature, humidity, speed, someone pressed the doorbell, these kinds of things. These are just some examples of places where a program might get information from. To get input from the user, one simple thing you can do in Python is use a function called input. If I say, let me say str1 gets input and hit the enter key, the input function will pause and wait for me to type some input on the keyboard. In this case, I am both the programmer and the user running the code, so I'm just going to type ASDF. That seems as reasonable as anything. When I hit the enter key, the input function gathers up that line of text that I typed and delivers that to be referred to by the str1 variable. So str1 now contains exactly what the user typed. Now, I hit the enter key when I concluded typing ASDF, but the input function peels off that new line character, so it is not part of the string that my str1 variable refers to. More commonly, the input function is used together with a prompt string. So I might say something like input, please enter your name. And input will actually display that as a prompt and then pause and wait for the user to type something. So I'll say John and hit the enter key. And now the name variable contains John. So here in slide 6 we have another example. S gets input, type stuff, and press enter. I won't bother with that. And we'll just say hello and press enter. Then we'll say print s has length len s. Aha! So we have actually just written a program. We have asked the user for input. We have read that input. We have processed that input by, in this case, simply computing its length. And we have displayed some useful output back to the user. Okay, so this recipe of get some input, do something with the input, produce some output is our general recipe that we're going to follow for very simple programs. Okay, so slide 7 repeats what I just said. We read some input, we processed that information, and we produced some output. All we have to do now is to put our program into some kind of file whose name ends in .py, and we will have actually written a Python program. So let's do that. Let me say file, new file. That pulls up an editor. And in my editor, let's have a comment saying file firstprog.py, and we'll say input, s gets the return from input, type some stuff and press enter. Now I put a space in here intentionally because I want the prompt to display a space following the colon, and then I'll say print s has length len s. Yay, my program. And I will then say file, save as, what do we call it? First prog. Yeah, first prog. And the editor, it turns out, will automatically add the .py extension, so I don't need to do that. All right, so I have now created my program, and I can run it by saying run module. Type some stuff and press enter. QWERTY. And I'm told QWERTY has length 6. My first official program. So the input function reads in a sequence of characters as a character string. But it's quite possible that your program is going to need to deal with integers or floating point numbers. You're going to have some way of converting among the different low-level data types. Virtually any kind of value can be converted to a string by applying stir as a conversion operation, a conversion function. So if I say something like stir none, well, all that does is to wrap the word none in quotes and make it a string. I can convert a floating point number to a string. So here I've got 12.354 times 10 to the 8th power. In this case, the stir function for float does not simply wrap quotes around the thing. What it does is it recognizes that that floating point number is not actually very large in size, and so it will reformat the thing without the exponent part. And so I get out 1,235,400,000.0 as my result. If you want to convert something to an int, you use the int construction or conversion function with some argument. Here I'm giving 4.567, a float, as my argument. You might think that the correct thing to do here would be to round up this floating point value to an integer 5. But the rule that the int conversion follows with a float is to simply chop off or truncate the fraction. So 4.567 converted to an int is just the int 4. The same thing is true for negative floats. Here I have minus 4.567, and if I convert to an int, again, the fraction just gets chopped off, and I have minus 4. I can convert a string into an int, assuming the string is a simple human-readable representation of an integer. So converting the string 456 into an int gives me 456. This int conversion is not arbitrarily clever, though. So if I say int of 11, in quotes, that's beyond the int conversion operator's reach, and I just get complained at that 11 is not recognized as a base 10 sequence of characters. Boolean values, it turns out, true as an integer is treated as 1, whereas false as an integer is treated as 0. Here on slide 10, we have some float and bool conversions. Converting an int to a float is simple. We basically just tack on a fraction of 0.0. However, beware that not all ints can be successfully converted to floats. Recall that 1234 to the 1234 power is an int value because int computations are arbitrary precision, but that number is too big to convert to a float, and so I get an error that that int value is too large. I can convert a reasonable looking string into a float, and here the float conversion is smart enough to recognize exponents. All right, so here I have as a string 5.432 e minus 10, so that's 5.432 times 10 to the minus 10th, I hope. And indeed, that's what I get as my float result. When you convert values to Boolean, it turns out that any form of 0 or any empty string is treated as false. So if I say bool integer 0, that's false. If I say bool floating point 0, that's false. If I say bool none, that's false. If I say bool and an empty string, that's also false. So these are examples of things that convert to Boolean false values. Any non-zero value and any non-empty string converts to true. So bool of 1 is certainly true. Bool of 1 times 10 to the minus 100 is also true. Even though that's a really small number, it's still not 0. Bool of a string containing a space is very definitely not the same thing as an empty string. So this string converts to the value true. All right, so we talked about the input function where we can ask the user to type something in. We can read what the user types into a string. And now we know how we can convert that string, assuming that the user types something reasonable, into a float or an int or a bool, let's say. When you're trying to process the input data, you may encounter various kinds of errors. And errors in Python typically do what's called raising an exception. For example, if I compute 7 divided by 0, we know that mathematically that shouldn't be defined, and we get told that this is an exception, namely a zero division error. If I say D gets list, it turns out that the list conversion operation requires an iterable rather than a simple integer as its argument. So I can say D gets list, if I could type, it would be helpful, range 5. All right, list is my conversion operation here, just like int or float or bool or stir is a conversion operation. And here I'm converting range 5 into a list, and that works fine. But as I said, if I say some incorrect kind of argument, like, 12.34, that is not, 12.34 is not an iterable, and consequently I get this exception. Similarly, if I try to convert a value to an int that just doesn't make sense, like hello, I get, in this case, a value error exception. And the same thing is true if I try to convert to a float, some string that just isn't in the right kind of format. Okay, so users are famous for making every conceivable error, and even inconceivable errors. So in order to protect yourself from users entering bogus data, you have to be prepared for these exceptions to occur, and you have to be able to process the exceptions to prevent your program from dying. The way you do this is to use what's called a try block, just consisting of the word try and a colon. Within that try block, you give whatever sequence of statements you want to perform. If one of those statements fails and raises an exception for some reason, you can catch any kind of exception by using the word except with a colon after it, followed by some cleanup kind of code. So let's take a look at this little example. I'm saying val gets 0.0 to create a variable called val referring to some number. Now I'm going to try to modify val to refer to 7/0. Well, I know that's going to generate an exception. I'm not permitted to divide by 0. I will then put in an except and set val equal to minus 1.0, assuming that the statement in the try block failed, which I know that it will. I want to make a comment about the indentation here. The indentation here looks a little fishy. Try is logically at the left-hand margin in terms of coding level. And therefore, I need except to line up at the same level. My problem here is that in front of try, the shell has chosen to display this prompt, 3 greater than symbols and a space, whereas in front of except, this version of the shell doesn't display anything. So despite how crooked that looks, I promise you that it is properly indented. The two val assignments are directly in line with each other. When I hit the enter key, I'm going to try to cause val to refer to the result of 7/0. That, of course, is going to fail. So down in the except clause, I'm going to end up setting val equal to -1. So when I display val, I see that val is -1 here. Okay, so I can get input from the user. I can attempt to convert that input into some form that I can use. If that conversion fails, or if something else about the user's input causes a failure that is an exception to occur, I can protect myself now by using this try-except combination. Another form of loop, by the way, in addition to for, is something called the while loop, which is somewhat less commonly used than for, but it's important to know about. The general structure of a while loop is you say while, and then you have some Boolean expression that results in a value that can be treated as true or false. followed by a colon, and then indented one level, you have a sequence of statements. The idea is, while this Boolean expression is true, we're going to perform these statements over and over again. Hopefully, there is something about these statements that will eventually cause the Boolean expression up here to become false. Otherwise, we will have accidentally created an infinite loop. So here is one example, one explicit example of a while loop. I'm setting a variable I to refer to 1 initially, and then I'm saying while I is less than or equal to 10. Okay, so while I is less than or equal to 10, I want to do something. And what I'm going to do here, just as an illustration, is to display the value of I, the value of I squared, and the value of I cubed. Now, at this point, if I just press the Enter key again, I would have myself a nice infinite loop. I would be 1 forever, and I would just keep getting 111, 111, 111, 111 printed over and over and over until I eventually got sick of it and pressed Control-C or even resorted to closing my shell window. To avoid this infinite loop, I want to be careful to increase I by 1. So in this way, the loop will only run through 10 times. I will start out being 1, and I'll display 1, 1, 1. That is 1, 1 squared, 1 cubed. Then I'm going to add 1 to I. 2 is still less than or equal to 10. So I'm going to display 2, 4, 8. That is 2, 2 squared, 2 cubed. And then I will be increased to 3. I'll display 3, 9, 27. And I is increased to 4, etc. So this loop is going to run through a total of 10 times. And I'll get 10 lines of output. There we go. So the value, the square of the value, and the cube of the value for values going from 1 up to 10. Okay, so as I've already said, users make all kinds of mistakes. When we ask the user to type some input, we hope that what they type is something that makes sense. But frequently it will be something that does not really make sense. So when we attempt to convert the string that the user typed into, let's say, an integer value or a float value, we're going to have to be prepared to catch value formatting kinds of errors with try and except. If we pass the try and except part of the code to indicate that what the user typed was at least correctly formatted, then we still may face problems with ranges. If we ask the user, for example, to enter their height, and they enter something like 5,000, 5,000 is certainly a reasonable format for a height, but it's probably not a reasonable value. So we will use just regular relational and logical tests to discover that that's probably not a good value and ask the user to try again. All right, let's take a look at a specific program that puts all of this stuff together. Here we have a program called user age, and this is available on Canvas. I have, in fact, already created a program containing user age. Let me open user age. And then we'll talk about this user age program. So let me get it over where we can see it. There we go. So here is our user age program. And before we even start picking apart the code, let me just run it. What this program does when I press F5 is it says, enter your age. And I'm going to say, well, I'm going to lie. I'm going to say 29. And 29 is a reasonable age in a reasonable range. It's not the correct age for me, but we don't care. And so the program succeeds and tells me that my age is 29. If I run the program again and type 29, well, that might make sense to me, but it's not going to make sense to the conversion function, the float conversion function that is trying to convert this into a floating point number. So I'll get told that I have a bad age format and that I should enter some value in the range greater than 0 and less than or equal to 125. This is not a wonderfully user-friendly program. It's using a particular piece of mathematical notation for a half-open range of values that I'm allowed to type. If I literally type 0.0, that's outside the range. It's correctly formatted, but it's outside the range. So I'll say something like 1.5, and that's with both correctly formatted and within the range. All right, so let's step through the details of this program. I'm starting out by creating a flag variable, so-called. Age bad is true. Age bad refers to true. That enables me, in just another couple statements, to say while the age is bad. That is, while the user has not yet typed an age that is correctly formatted and that is also within a reasonable range. So this loop is going to run over and over and over and over again until eventually we hope age bad becomes false. We're going to start out with the age variable containing the floating point version of the user's age set to 0.0, which is a value that's outside of our legal range. Now, various things can go wrong when we ask the user for input and the user provides us with some input. So we are going to try to get the user to enter their age as a string, and then we're going to try to convert the string that they typed into a float. Now, the user might not type anything. The user might type something that's valid. The user might type something that's not valid. The user might press Control-C or something along those lines. So there are a whole lot of ways that this can fail here. But when I run my program, let's go ahead and do that again. When I run my program, we see that we're in the while loop while the age is bad, and at this point the age is bad. Try to get the user to enter their age. All right, so I'm going to type 53. Still not correct, but what the heck. The input function is going to receive and return that string of 11 characters. Okay, so 50 is 5, 3 is 5, and there's a space in between, so that's 11 characters. And then float is going to fail in converting that into a floating point value. So, because that conversion fails, I drop into the accept block of code, and I display bad age format. Not a very user-friendly message, but nevertheless it gets the point across, I guess. And we're going to force the age to be some invalid value, -1 in this case, so that below the accept, because the age is not, notice that we're using not here, and not has low precedence in Python, because the age is not within this valid range of strictly greater than 0 up to less than or equal to 125. Because the age is not in that range, we'll display our helpful message telling the user to enter a value that's in that range. Okay, so since this test is true, right, age is -1, so this test here, whether -1 is strictly greater than 0.0 and less than 125.5, that thing is false, but not false is true. Therefore, we say enter the value between 0 and 125, and we don't perform the else part, and we go back up and discover, age is still bad. So age is bad, and we're going to try to ask the user again, enter your age. All right, this time I'll say 53.7. And when I press the enter key, that string of 4 characters becomes the value of becomes the value that age stir refers to. And when I then convert that to a float, this time it is going to succeed. Age will be set to 53.7. Since age is set to 53.7 successfully, I skip over the accept part. I discover that the age is within a valid range. All right, so this test is true, and therefore not true is false. And I drop down to the else part, and I set age bad equals to false. Well, now we go back up to the top of our while loop, but since age bad is false, we're done in the while loop, and we drop down to the next statement following the while loop. The next statement following the while loop is the one that's indented at the same level as the while loop itself, which is simply this print statement, and so we display age is 53.7. Okay, so there's a fair amount of machinery going on in there. We have variables, we have some arithmetic, we have some comparisons, we have an if-else, we have a try and except, we have a loop. But each one of the pieces, I think, should make sense at this point. Okay, so that is the machinery for handling some user input. Next up, we're going to take a look at defining simple functions. If you have some kind of formula that you apply over and over again, rather than repeating all of the code for that formula, it's a good idea to store that formula into a function that you can simply call. Okay, so here we have a sequence of 3 print statements in which we're using our Fahrenheit to Celsius conversion formula. So if our Fahrenheit temperature is 78.9, then the corresponding Celsius temperature is 5/9 times the quantity 78.9 minus 32. Likewise, if our Fahrenheit temperature is 43.2, we have the same formula. The only difference here is that we plug in 43.2 rather than 78.9. And then finally here, we're converting minus 12.5 Fahrenheit. And again, we have the same formula. Now, this, of course, works, but it's very painful and very error-prone to have to retype the details of this formula over and over and over again. So what we'll do is to create a function. We're going to define a function using the DEF keyword. Following DEF, we give the name that we want our function to have, and then we're required to give parentheses. Optionally, within those parentheses, we can specify one or more arguments that we want the function to receive. And just like a for loop or a while or a try, this thing ends with a colon. Underneath the colon, we have a sequence of indented statements that presumably make use of these arguments that have been passed in, and that in our case, we want to return the Celsius temperature corresponding to the Fahrenheit temperature that was passed in. Okay, so here we have created a formula called F to C for converting Fahrenheit temperature to Celsius temperature. The argument we're going to call F, meaning Fahrenheit, and we're going to return the corresponding Celsius value, which is 5/9 times the quantity, whatever F is, minus 32. All right, so if we set the Fahrenheit temperature to 43.2, we can then display the temperature, the string Fahrenheit is, and then we'll just call F to C with the value 43.2 as the argument. This formula will be performed, and the result of the formula will be returned right to this place where the function was called. And so that value then that was returned will be passed into print to display the correct stuff. Here, to sort of extend our example, we're actually calling our function within this print statement in a for loop. Okay, so let's first define this function. We're going to define f to c of f to return, let me make sure I got the formula right here, 5/9 of, or times, f minus 32.0. Okay, so there is my f to c function. If I call f to c with some known Fahrenheit temperatures, like 32 degrees, that should correspond to 0 degrees Celsius. 32 degrees is freezing in Fahrenheit. 0 degrees is freezing in Celsius. And sure enough, that works. If I say F to C 212, well, that's boiling in Fahrenheit. And in Celsius, that should be 100. And that also works. So if it works for two values, it must work for every value, right? Well, perhaps not. But in any case, let's try our for loop here. For t in range. Now, minus 40 is the one temperature where the Fahrenheit and Celsius scales match. So if I convert minus 40 Fahrenheit into Celsius, I should get minus 40 as my result. 110 is a fairly hot Fahrenheit temperature. 10 degrees is our step size in this range. So let's see what we get when we do these conversions. Okay, so I'm going to hit my enter key twice. Once and then again to persuade the shell that I'm done typing in my loop. And so for this range, starting from minus 40 and going up to but not including 110, with a step size of 10 degrees, I see that minus 40 is indeed minus 40 Fahrenheit is indeed minus 40 Celsius. 0 Fahrenheit is minus 17.7 Celsius. 30 degrees Fahrenheit, which is just a little bit below freezing, is minus 1.1 Celsius. And so on, up to 100 degrees, which is 37.8 Celsius. Okay, so that's an example of a function definition, and we've used a for loop on a range to display a table of conversions of Fahrenheit to Celsius. If we want to get input from a file, we're going to need to use a function, a built-in function named open. And the open function will take as its first argument the location on your system and the name of the file that you want to use for input. Now this is a generic example here on slide 19. Let me open a specific example. I have a file that works on my system. All right, the name of this program is copy file open close, because what we're doing here is we're copying a file and we're using the open and close functions. So here is my version of the program copy file open close.py, and in here I have specific directory names and file names that do exist on my system. Now, this program is going to be available for you to make use of but you will have to modify the locations of the input file and the output file that you want to create so that it works on your system instead of on my system. Okay, so we're going to open some input file. On my system, there is a file named expenses.txt, which is contained within a subdirectory called my-IPP-dir, IPP for Introduction to Programming with Python. That in turn is under my personal directory in the users directory on my C drive. Notice that even though I'm running Windows, Python allows me to use slashes as the directory separator when I type a file path name. Slashes are easier to use than backslashes because backslashes are special characters inside of a string. And so if I wanted to use backslashes instead, I would end up having to double all of the backslashes in order to get this to be equivalent. Okay, \n is a new line character, \t is a horizontal tab character, \/ is a literal backslash character, and I'm much too lazy to have to remember to type backslash twice, so I will just use / instead. Okay, it's just easier. What I want to do is to open this file for reading text. So the second argument that I specify to open is the mode in which I want to open this file. That file already exists, and I want to read text from it. It turns out that this file contains ASCII characters. I'm going to specify as my character encoding alphabet UTF-8. Now, UTF-8 is one of the Unicode character sets, and it turns out that UTF-8 is an 8-bit character set that contains within it the 7-bit ASCII character set as a subset. So if I have an ASCII file, which I do in this case, it's safe for me to use the UTF-8 encoding in order to open that file and read data from it. Now, I don't want to display info from this file on my screen. What I want to do is to write a copy of this file into an output file. So I have a second open function call here. This time the variable that's going to be created is fout. So fin is my input file, fout is my output file, and the mode wt is how I tell the open function that I want to write text into this file. Now, in this case, you have to be a little careful because if the file here, expenses_copy.txt, already existed, this open function is going to wipe out whatever contents expenses copy used to contain and set it up to have new data written into it. All right, so whatever used to be in that file, if that file already existed, is now going to be wiped out and replaced with new output. Since I read ASCII characters from the input file, I'm also going to want to use UTF-8 because I'm writing ASCII characters to my output file. Now, when you open a file for reading, that file is an iterable. And so you can use a for loop to step through each of the lines in that iterable. The for loop will read one line at a time from the input file, fin, and I'm going to turn around for each line that I've read from fin and write that line to my output file. Okay, so every line coming from the input file is simply going to be written as is to the output file, which means that the output file should be an identical copy of the input file when this is all done. The last thing that I need to be very careful to do in this program is to close each of the two files that I opened. I need to close my input file, and I also need to close my output file. Closing the output file is the most important thing to do, because if the program were to simply die without the output file having been closed, you might discover, when you looked at the output file, that some of the lines at the end of the input file hadn't yet successfully been written to the output file. So the output file might be a partial copy of the input file rather than a complete copy. Using close on the output file forces that output to be completely written, and then the file is going to be closed. Let's see whether this actually works. Let me pull up an ordinary terminal window that I have. This is a window that behaves like a Linux terminal. And in here, I can use ls to see that I do have this file named expenses.txt. And I can look at that by saying more of expenses.txt. And what this file contains is a bunch of money amounts, categories, dates, and descriptions of various expenses for some small business. As it happens, I also already have this expenses copy.txt file. Let me remove that. To make sure that my program is actually creating it, and it's not just an illusion. Okay, so here is my input file, expenses.txt, and my output file is going to be expensescopy.txt. Let me now run this program by saying F5, and being it happens really quickly, if I display all of the files in my directory whose names start with expenses, I see, yes, I do have the expenses copy.txt file, and it is indeed September 5th, 2019, just a little after 11 p.m. right now. So expenses copy.txt does contain an identical copy of the input file, expenses.txt. Okay, success. All right, now I'm going to tell you what I call Ostland's Law, which is that doing two things in order correctly is about 4 times as hard as just doing one thing correctly. And anytime you use the open function to open a file, you have to remember later to use the close function. And even if you're a very experienced programmer, it's surprising how easy it is to forget to put close at the bottom of your use of a file following the open. So as an alternative to having to use the close, another way of using open is to use this thing called the with statement. The idea here is we're saying with, open this file using the same arguments that we did before as fin. Now, the whole purpose of using with is that I am going to end up opening the file. I am going to be using fin as the name for my input source from this file. But using with eliminates the need to do closes. It turns out that closing is automatic as soon as you are finished running the code within the with. All right? So I'm saying with open the input file as fin, do some code. Well, the first thing I'm going to do in there is with open the output file as fout. do some code? Well, the code that I'm going to run here is to get each line one line at a time from the input and write those lines to the output. And that's it. Once that code is done, once that loop is finished running, Python itself will have arranged for the output file and the input file to automatically be closed, and I don't have to remember it myself. All right, so if you get used to using with, that eliminates the need to remember to do close each time you do open. Let's take a look at that program. I will open that program. This program is copy file with, and here it is. And in my case, the files, the input file and the output file, are files that actually exist or that I can actually create on my system. Now let me get rid of, ls-l expenses star. Let me get rid of expenses copy 2, which is the output file that this program is going to create. I'm going to remove expenses copy 2. All right, it's gone. And now I will run my program by pressing F5. Happens really quick. And I do indeed now have expenses copy 2. And you can, it's the same as the expenses.txt file. Okay, so that gets us to the conclusion of this second week 2 lecture. We've talked about what's involved in writing a very simple program. That is, you create a file whose name ends in .py. Within that program file, you have to get some data from somewhere, process that data in some fashion, and produce some output that's of some use to somebody. Along the way, you're going to need probably to do conversions. Particularly if you're dealing with user input, you're going to have to deal with exceptions if the user types bogus input. And very likely you're going to have to deal with either input files or output files or both. In which case you need to know about open and close or with open as an alternative to open and close. All right, so that is that.